welcome to our session on arithmetic, specifically addition in digital logic circuits. Today we'll be looking at how to express addition and implement it using the logic gates we've discussed in previous sections. As a review, addition in base 10 is relatively straightforward and is similar to the way addition in binary or base 2 is conducted. Fundamentally, in addition, when we add two multiple-digit numbers in base 10, we have to consider that each addition operation will generate an overflow, which we typically call a carry. In this example where we add 77 and 23, when we add 7 and 3, we'll get 10. Now we can't have two digits in a single position, so we'll have to carry that one to the next most significant column to the left. Then when we add 7 and 2 and add 1 to that, we'll get 10 again. Again, we can only put one digit in that position, and we'll carry the 1, which will be the last digit or most significant digit in this operation. And not surprisingly, 77 plus 23 is 100, something we can all do without our calculators. Base 2 is very similar, except it's much easier to generate a carrier because we only have two digits to work with. In this example, 1 plus 1 gives us a 1, 0, but we can only place a 0 in the least significant bit position, and we carry the 1. 1 plus 0 gives us 1 with no carry. 1 plus 1 gives us 0, again with a carry of 1. And 1 plus 1 again gives us 0 with a carry of 1. So our result when we add 0, 1, 0, 1 plus 1, 1, 0, 1 gives us the result of 1, 0, 0, 1, 0 in base 2. So addition is very similar and straightforward to implement in base 2. Let's take a look at how we actually implement this in logic gates. So we'll start with the half adder that only has two inputs, A and B, and two outputs, a sum and a potential carry. Since we only have two inputs, we only have four possible input combinations, and we can easily find the sum and carry for each. For example, in the second line of our truth table, 0 plus 1 gives us a sum of 1 and a carry of 0. 1 plus 1, on the other hand, causes an overflow, so our sum is a 0, but the carryout is a 1. Using this truth table, we can generate two 2x2 Carryout maps to find the sum of products expressions for both sum and carry. For sum, we have two 1s that are not adjacent to one another, so we have to generate a term for each. Sum is simply equal to, from the Carryout map, this grouping, which will give us A naught times B, and this grouping, which will give us AI times BI naught. So our sum of products expression is AI naught, BI, or AI, BI naught. Now this should look familiar. This is simply the XOR function. So we'll write this over here as a simplified expression for the sum, AI XOR BI. So that's our expression for sum. For carry, we have an easier Carryout map. There's only one 1 to look at. And the expression for that carry bit will just be AI and BI because they're both equal to 1. Now implementing this should be fairly straightforward. And the first, to generate the sum, we'll just XOR A and B. And that will produce our sum output. And to generate carry, we'll just AND together AI and BI, and that gives us our carry out. So that is the solution for the half adder. Now the difference between a half adder and a more complicated full adder is going to be that we have to consider in any addition operation that there's actually an input carry. And instead of adding just 2 bits, we'll be adding 3 bits. So in full adders, we add the additional input, the carry in bit, and we can generate the truth table now of all 8 possible input combinations in adding those 3 bits. And just like in the half adder, we'll have 2 outputs, a carry out and a sum out. Once we know the truth table, we can generate the 2x4 Carryout maps both for the sum and the carry out. The sum will have no groupings greater than 1. And the carry out will have 3 groupings of 2 to obtain the simplified sum of products expression. So for the sum of products implementation, we expect that the sum will have 4 terms since none of the ones can be grouped into more than a group of 1. So they stand in isolation. And the sum expression will simply be A naught, B naught, C for the first grouping of 1, or A naught, B, C naught, where all the C's are the carry in. For the next group, A, B, and C. And the last group is A, B naught, and C, where all the C's are carried ins. Now we can simplify this, or we can look at this very interesting arrangement here that looks remarkably like an XOR. And once we simplify S, we'll find out that it is indeed an XOR pattern. And sum is just equal to the input bits XORed together. The carry bit has these 3 groupings of 2. In the carry out, we would expect 3 terms, each containing 2 variables each. This first grouping will simply be B times Ci. The next grouping here will be A and B. And the last grouping here will be A and Ci. So these are our expressions for the sum output and the carry output of our full adder. And now we'd like to go to implementation. Now if we implement now, we'll have 2 XOR gates to generate the sum, and we'll have 3 AND gates and an OR gate to implement carry out. But let's see if we can simplify carry out a little bit further with the goal of minimizing the total number of gates. So carry out has these 3 terms in it. S we've already discussed is just 2 XOR gates. So let's copy that in here. We just XOR all the input bits together in pairs. And now if we look at CO, if we're clever, we can go ahead and start separating the terms and expanding them in an effort to identify some overlapping functions between carryout and sum. So just to show one step of this process, we can pull B out now and distribute it. But now we can apply the Boolean identity that A or Ci is also equal to A or A not Ci, and that will come in handy as we try to simplify this expression and reduce the total number of logic gates to implement this full adder. So if we implement that here, we'll get B times the quantity A or A not Ci or ACI. And as we continue, we can now distribute this out again as AB or A not BCI or ACI. Now it does look like we're making a big mess, but if you can be patient, let's do one more distribution here. Take A out and multiply times the quantity Ci and leave our 3 variable term by itself. Now we can use this same identity to say that this is A times the quantity B or B naught Ci, or A naught B Ci. Multiplying out, we can get AB or Ci times the quantity AB naught or A naught B. And this should look familiar as the XOR function. So now we can say that our output CO, is just equal to A and B, or Ci times A XOR B. And since we're already using A XOR B in sum, we've saved a logic gate by making that XOR gate redundant in CO and S. So let's look at the implementation now in actual logic gates. Sum is simply A XORed with B, and then once again XORed with C to obtain the output sum. But now we can use this output of the first XOR gate to AND with Ci, and then we'll OR that with A and B. We have two AND gates here, and finally an OR gate, which will generate our other output, CO. So this is the implementation of the full adder with a minimum number of gates. We have one OR gate, two XOR gates, and two AND gates here for a total of 5 gates. That's pretty good for the implementation of a full adder. The 3-bit adder now, we can start putting together building blocks. In the first operation, the least significant bits when we add them, notice that Cin is connected to ground because there's no carry in on the first operation, and it's actually equal to 0. Now given that, we could actually replace this with a half adder if we wanted to be really efficient. But often it's much easier to just duplicate the full adder multiple times to get as many bits as we need in our ultimate addition goals. But let's take a look at what goes on with the 3-bit adder. There's nobody detecting a possible overflow at the inputs. So there's some cases, such as when we add 6 plus 6, that we get an overflow. If we add 6 plus 6 here, 1, 1, 0, 1, 1, 0, plus 1, 1, 0. What we'll get at the output, if we just look at the 3 output bits, is 1, 0, 0. Now that carry out from the last full adder is essential to make sure this result makes sense, because that carry out is equal to a 1, and that's what gives us our accurate result of 12. So it's important when we work with full adders that we also consider the overflow. And this will become especially important when we do subtraction, where things aren't so intuitive. So in this session, we've taken a look at how to add using both half adders and full adders. Now, full adders can be used to perform addition, or they can be used as building blocks for other functions like subtraction, multiplication, and other arithmetic functions. Full adders can be made out of gates, as we discussed in this session, or it can be put together using multiple half adders. And that's all for addition and adders today. Thanks for joining us as we continue to explore the world of digital logic and circuits, and we hope you'll join us again soon.